first underwater target, she's provided much valuable information for anti-submarine tactics. Her fuel is described as high-test peroxide, which is not to be confused with the stuff used by ex-brunettes.
But the HTP was extremely volatile, and the technology was a dead end.
By 48, there's a submarine officers conference, which is held regularly, and they're all complaining. No one helps them, the stuff is terrible, they can't get the materials, no one wants to do it. And then someone else walks in, it's Rickover.
Hyman Rickover was a brilliant engineering officer in the United States Navy. He believed that the future of submarines was nuclear.
This chart shows that 1 pound of uranium is equal to 2,600,000 pounds of coal. Here's the pound of uranium, which in comparison is so small that it's represented by a pinpoint.
Here was a fuel that didn't need oxygen for combustion, one that freed the vessel from the surface. By generating its own air and by purifying seawater, the submersible could become a true submarine.
Rickover did one unbelievably important thing. About 48, 49, he had a series of design studies for maybe the next step in reactors. And it was very easy to imagine pushing this technology slowly onwards, and maybe eventually you would do something with it, but it wasn't that mature technology. You could keep pushing a lot longer. Rickover said, no, it's mature enough. We're going to go now. It was obviously Rickover's perception that nuclear gave a new dimension to submarines, and for that matter, surface ships, and that if he did it right, there would be an unbelievable advantage for the Navy.
The result was a new age in naval technology, launched by Nautilus, the world's first nuclear-powered submarine.
This wasn't a hot, sweaty diesel submarine. This was just a luxurious boat that was clean, neat, very comfortable to live on, had an abundance of water. Everybody smelled good, and it was just happiness here.
In 1955, Nautilus made all conventional submarines obsolete. She was the first to be designated SSN, the N for nuclear.
I reported aboard the Nautilus in March of 1957 and served under Admiral Wilkinson. And later that year, we went up under the ice for the first time. And this mission, when we had left Seattle, was announced as a top secret mission. The cover story was we're heading south and going down to the equator, then going to go back through the Panama Canal back up to home in the Atlantic.
The real mission was to attempt the first underwater transit from Pacific to Atlantic, feeling their way under the polar ice cap. This was the Cold War between the Soviet Union and the United States. Being the first to develop new technology was the key for both sides. The success of Nautilus would be a PR coup for the U.S.
When we left Seattle in 1958, one of the announcements that Captain Anderson made was that our job was to out-Sputnik the Russians. After we had surfaced in the Atlantic side, one of the things that everybody realized from a strategic standpoint is that we had been in their backyard.
When they arrived in New York Harbor, they were met with a spectacular reception. Nautilus had become a symbol of American know-how, navigating the last unexplored corner of the planet.
We didn't really know what the impact was. We had no sense of how important the trip was. We knew everybody would rejoice and everybody was happy for us, but we did not fully understand the strategic impact, the economic impact, if there is one.
The impact of the atomic age was a submarine that could go for months without the need to surface. Her only limitation was the amount of food she could carry for the crew. But the ability to stay submerged and cruise at high speeds created a demand for new hull designs.
How do you learn how to control these things at high speed underwater? And how do you learn how to control them before you actually spend on building a fast one. So the question is, how can you build something fast enough that it will simulate a fast sub like Nautilus, and yet doable without Nautilus power plants? Well, they go to David Taylor Model Basin, and they say, find us the most efficient underwater hull form. We don't care if it's very good for a combat sub. All we want is something real fast. They do a series of experiments in their test tank. They find out that the most efficient hull form is what's called a body of revolution.
The result was the Albacore, now on display at the Maritime Museum in Portsmouth, New Hampshire.
By term body of revolution, well, I think you can see it the most graphically if you get out an imaginary knife and slice through this piece of baloney we call albacore hull, like so. In every section that you slice through would be a circle.
Designed to operate a good deal of the time on the surface, is on the way out. Submarines of the future will be true submersibles, designed to operate underwater 99% of the time, and will be shaped like a streamlined whale.
The streamlining reduced drag, helping Albacore achieve record submerged speeds. Now the crew needed to figure out how to handle her.
It was remarkable. It could start from dead in the water and be to maximum speed in a matter of minutes. Now, the advantage there is obvious. If you're trying to escape or trying to attack or even trying to transit, high speed from the get-go was essential.
This is a Navy picket boat. It is traveling at twice the speed of the fastest World War II submarines. The Albacore's speed, like that of the Nautilus, is highly classified. The Navy says only that it exceeds 20 knots.
There he is. Mark, bring me up about a foot. About a foot, aye.
As you watch the Albacore's periscope overtake the picket boat, you may get some idea of the speed of the atomic submarines of the future.
Control was critical, since turning at speed could put the submarine into a sharp dive and send it below crush depth.
We had a little dorsal rudder behind the sail, which was to overcome the JC, and excuse me if I offend anyone, the Jesus Christ factor, because when we hit a curve at high speed, you went literally into a snap roll. And we took several deep roll dives, as we called them, down to about 54 degrees. Imagine standing at 54 degrees. It's quite a lean. So we learned if we were in a dive and high speed, throw the rudders over and you'll come out.
The Albacore has been a dream of man for more than 400 years because she flies underwater. She is the true submersible. And when the Nautilus nuclear heart goes into the Albacore form, man will never worry about coming to the surface to breathe and to look about.
The marriage of the Albacore shape with the nuclear plant of Nautilus resulted in the skipjack class, the basic shape and power system for all submarines since.
Other than the fact that you are now in a nuclear submarine that has made a quantum leap toward being a true submarine, limited only by the food supply, the next event that you can look at is the evolving of the weapons systems on that platform.
The final stage in the development of the modern submarine was once again about marrying platform and weapon. Missiles were first tested in World War II when German scientists produced the V-1 and V-2 rockets. The Allies realized that missiles would give the submarine a crucial new capability to attack land targets.
At the end of the war, we're interested in experimenting with missiles fired by subs. In fact, the Russians are also. By '48, we have contracts out for next generation, and we build a missile called Regulus. Regulus is subsonic. It flies about 600 miles. The problem with Regulus is it takes a fairly large